and the effective radius, which suggests more of cluster properties determining the age of the ICL rather than BCG properties determining the age. We do the same thing for metallicity slopes, right? Looking at properties of the BCG on top and properties of the cluster on the bottom. And again, we find no obvious correlation with BCG values, okay? So the slope of the metallicity profile doesn't seem to care about what the BCG is like. But a mild correlation with cluster velocity dispersion and cluster X-ray luminosity, which are both proxies for cluster mass, close bracket, do appear. We can look a little bit deeper at the stellar populations because the models that we use give not the average population for that fiber, for that region, but give like the fraction of each type of stellar population that is required for the best fit. So when we do that, we can compare directly the ICL stellar populations to the core populations in this figure to notice how different they are. The core is made up of mostly very old, very metal-rich populations, and the ICL has a huge component of young metal-rich and metal-poor stars. Okay? There is some overlap between the two, and I mean, certainly the ICL has some contamination from the BCG as well, but they have different populations. Poor stars are much more common in the ICL than the BCG, and these stars presumably then formed in shallow potential wells. So this supports a merger and tidal disruption scenario of the ICL. And given the mass-metallicity relationship and the metallicity of these stars, L-star galaxies fit better with this data. L-star galaxies being the source of the ICL, than large red galaxies. Okay, the final property we're going to compare is the velocity dispersion. So to look a little bit at the kinematics, so moving away from the stellar populations. So BCGs in massive, relaxed clusters have velocity dispersions that rise sometimes to the cluster value. So it'll take me a couple slides to show that. But here's our sample. And I don't think I mentioned this before, but the X-ray bright clusters are on the top and the X-ray faint clusters are on the bottom. Here is our line where we think the BCG and ICL are becoming distinguishable. And you notice at this line we see a lot of sharp upturn. Okay? So to values of several hundred kilometers per second. There's a team in Berkeley, led by Professor Ma, who had put out a series of papers, massive, which is a series of papers where they have a similar technique as us. They use an IFU with fat fibers, they make regions, they look at the properties of the BCG as a function of distance from the core. They are looking at a huge mass range, and in their most massive bin, there live a few BCGs, okay? That's different than ours because we are looking at just BCGs. But they have a few BCGs in this most massive bin, and you can see in a few of their galaxies, they see this rise in velocity dispersion as well. So we do the same thing, we parameterize the difference with the slope, and we look at the slope of the velocity dispersion with BCG properties and with cluster properties. When the slope is positive, so when the velocity dispersion rises, there's no obvious correlation with any of the BCG properties. Any correlation with cluster velocity and velocity dispersion and X-ray luminosity is less obvious, but in the next slide I'll make a case for what's going on, what I think is going on. I'm going to take a moment here to say, when we were going into this, we thought maybe the BCGs that were far away from the cluster core might be the ones with falling velocity dispersions, right? Like maybe we're so far away from the galaxy cluster core that those stars aren't following the cluster profile. They're connected to the galaxy profile. We didn't really see that here, which is kind of surprising. Okay, so if we look at just these BCGs with rising slopes, which are the black dots, and we plot the velocity dispersion of the cluster and the velocity dispersion of that outside point, the ICL, and I draw a one-to-one line as the black line, these points are beginning to come up to the cluster value. Okay. There is one really well done spectrum out there on Abel 2199 that Ralph Bender did a few years ago that goes really far out, like to like 80 kiloparsecs from the BCG core, and they see a rise up to the cluster value. There have been a lot of studies since going back to the 70s that look at the velocity dispersion as a function of radius, mostly just out to 1 times the effective radius, however, and they find a mix. They find some rising, some falling, some flat velocity dispersion, and rarely to the cluster value if you're only looking within 1 RE. For these galaxies with the positive slopes, there's been enough time for the stars to fall into the cluster potential. If I plot the velocity dispersion slope, okay, so is the velocity dispersion rising or falling, and the ratio of the BCG core velocity dispersion, so the influence of the BCG, divided by the cluster velocity dispersion, so the influence of the cluster's potential, I see this trend. And more specifically, if the cluster dominates, I have rising slopes. And I only get these falling slopes when the BCG dominates. Okay, so this is what I think this is what we're seeing. And these are the galaxies we're probably getting far enough into the ICL that we're getting a significant ICL signature in our spectrum. So, a proposed relationship between the BCG and the ICL. Okay, the brightest cluster galaxy and the intercluster light tend to have different properties. Brightest cluster galaxies, their cores are older, they're more metal rich, and they have lower velocity dispersion compared to their surrounding ICL. These differences, we parameterize them with a slope, and this slope is determined by host cluster properties, not BCG properties. In many cases, the intercluster light velocity dispersion matches the dispersion of the host cluster, a really nice signature saying that these stars are part of the cluster. They're following the cluster potential. So this suggests that the BCG and the ICL have different origin. The BCG formed first. When we look in detail, we find that 87% of the stars are over 10 billion years old, corresponding to a formation redshifts of about Z greater than 3. The intercluster light is younger, therefore the stars formed after the BCG stars, and the wide range of ages in the ICL suggests a slow formation process taking place over a long period of time. The intercluster light belongs to the cluster and should not be seen as a component of the BCG. If we come back to the cartoon we had before, and make it not for elliptical galaxies in general, but specifically for brightest cluster galaxies, okay? Maybe we are at the compact quiescent galaxy phase a little bit earlier at redshifts of 3. And when we think about this dry merging stage, some of these minor mergers are going to come in onto the BCG and form the lower metallicity outskirts of the BCG. And some of these minor mergers, which for BCGs can be L-star galaxies, because BCGs are so massive, are going to be, the stars are going to be stripped or shredded and make the ICL. So this dry merging process we should think of as growing the BCG's mass, and also creating the ICL. So here's my speculation. The ICL could originate from intermediate mass galaxies, destroyed by the tidal field of the BCG itself, and this would explain why the BCG is always older than the ICL. Final slide, what's next? There's a wealth of data with this, ISU set that we have taken 4 years to collect. Our next paper is going to be about close companions. Okay, so we're going to use the kinematics to figure out how many of the projected companions are real companions, calculate dynamic friction time scales, see how much the BCG might reasonably grow in about half a billion years or a billion years. We're also going to investigate the emission line properties. A large subset of this system, like these are massive X-ray clusters, a large subset of these BCGs have emission lines in their cores, and a few that extend into the fibers surrounding the core, so we'll take a close look at those later. And also we have joined the MANGA project with as the SCSS through FAST, which is a program that aims to involve undergraduate serving institutions like Cal Poly. So I call this part the if you can't beat them, join them part, because it took us 4 years to collect the data for 23 BCGs. And MANGA has 10,000 galaxies that it looks at with a very similar IFU built by the same guy who built SparsePak. And they have like half their galaxies already. In there, there's probably about 50